Can you hear us? We got some technical issues. I hope not.
They never taught us what ground was. We had to figure it out for ourselves. We had to ask.
I can hear, but it's pretty quiet. Yeah. All right. And now we can hit countries.
All right. Welcome, everybody. We're going to start the session. Thank you very much for coming. This is ELSOC. Thank you very much for coming. I'm Otto. This is Sudarshan. We're going to run this for you. Let's do our best for the lab test, right? So, the way this is going to go, I'm just going to cover over a couple of different declaration types and how we implement that in code. After that, we're going to run through a couple examples, how we make our test benches, and then Mark's decoder, I'll switch between me and Sudarshan, and then finally we'll get on to the past paper, well, the sample paper for the lab exam. All right, let's get keen. So, first things first, we're going to begin with some behavioral modeling. So, behavioral modeling, in case you forgot, it's always within, always at triggers. We define the behavior in the model as like what goes in, then what should come out, okay? It's very much disconnected to gates. It's just what's happening, and let's try and identify that. So I'm gonna go ahead and do a little modeling one. Yep. Behavioral. Let me actually just put this in. All right. So in these instances, we use output registers, and we also use just general inputs. Okay, for this example, what I'm going to do is just do a pretty much example NAND gate as a behavioral. Okay. All right, if you guys have any questions at any point with how we go ahead and run these, please go ahead, shout out, and let's get that moving. So, NAND gate, all we really want to know is how we do it behaviorally, and behaviorally is going to very much concern with just if-else statements and conditions. So, the instance that we're going to use here is we're going to go always at the inputs. So this is just tracking the inputs. We're going to run through the cases of the inputs. And then that's just going to follow a binary pattern. Since we have two inputs, I can define binary cases as such. Now, mind you, this may be not the best implementation of this type of gate, but we can go ahead and try and speed things up. For this type of gate, a NAND gate, we know that, quite frankly, using something a bit closer to data flow modeling or structural modeling might be a lot faster, a lot nicer, just because it's already been implemented for us. Okay? So we go ahead, NAND gate just means that it is always one unless it is both. Okay? So here we have our NAND gate. We can then end case, and then end module. All right. So this is how we would run that. That is behavioral modeling. When you run through different sources, just recall, run through your lab stuff. We always want to create a new source. We go through a Verilog module, give it a name.
For a quick bit of context, we are using a slightly older software in the demonstration. You're using Vivado. Most of the controls are basically in the same place, but this just looks a bit 15 years older. Works the same language.
Yes. So we are using a bit of an older software, but basically the same in all the implementations. All the code should be very much the same as well. So we're just going to do structural modeling as an example. We run this through, next, finish, and it creates it for us. So structural modeling, just a little rundown. It's very much in the idea of here's how we are going to place wires into our different kinds of stuff. Yeah, let's go. Function FH. All right, thank you. So structural modeling, it's how we go ahead and place wires in a schematic. So an example I'm going to show you guys is a silly kind of adder structure. Okay, so silly adder. And what I mean by placing wires and stuff is we'll define in our inputs in the declaration of the function, the outputs being output out, output carry, input A, input B, and input C. All right? No, you cannot. Inputs are not registers. Registers are what you really store things into. So, yes, you can. So that's really just the formation of your code. Registers, they store bits. Output, just like I hold on to it. And it's very much in the sense of flip-flops that you'll use. However, inputs, and if I just say input and output, it's very much just a logic-based decision. Okay, this thing turns into that thing because of whatever interior logic that we have. All right, thank you very much. So, moving forwards, I've declared my inputs and my outputs. Now, because we're using structural modeling, something that we're going to need to do is define some wires. Okay, so I'll just begin with a wire set. I don't know how many wires I'm going to need right now, but I can pretty much determine that for an adder, mind you, this is for a full adder, we're going to have the carry is equal to at least 2 bits active. That just means A or B, sorry, A and B, A and C, or B and C. And then we also say that the output is just going to be at odd parity of bits. So if I'm adding together an odd number of ones, I'm going to get a 1 at the output of this adder. All right? All following? All right. And so to do this, first things first, it might actually be easier to go ahead and implement it as a data flow modeling. So typically when going from data flow to a structural or vice versa, we really want to see what's the big equation first, and then we can break it down a lot nicer. So you can see here I've gone ahead and defined some logic things for the carry and the output. So what I'll do instead is go ahead, create another source, and once again, Verilog module. I'll make it a data flow model. All right. And we're just going to copy over most of the things we're doing, but there's a couple differences between, our structural modeling and the data flow modeling. So let's see what we can go ahead and copy over. All right. Yes, Sudarshan, I do need help zooming in. All right. So data flow modeling, essentially, the inputs to the module, we're going to define slightly differently, okay? We're going to define them just inside here. So we're going to have an output, a carry, A, B, and C. And then within this module, we're going to define that the outputs are going to be the out and the carry, and the inputs are going to be A, B, and C. Now, in our data flow modeling, something to note is that we really just go ahead and call gates via symbols, okay? So we have a symbol for all these different types of gates. We have the AND gate, which I just shift 7, just the AND symbol. We have the OR gate, which is the vertical bar just underneath your backspace button. We have the XOR gate, which is an exclusive OR. And then there's one more, which is just the NOT gate, which is the total. Pardon? We could do that very much the same. I'm just showing different ways that we can go ahead and define things. So we've defined the gates, and we know how to do this. So what we can actually do is just use our fancy little assign statement. So we're assigning the output to be equal to. We know the output is just going to be the odd parity. Odd parities are very cool with XOR gates. You could implement it in other ways, just using midterms and max terms. But if we're looking at this from a data flow perspective, fewer symbols makes it easier for us. So I could just do A or B or C, all XOR'd together, all right? Alternatively, I have my carry statement. Now, carry, I said I need at least 2. Now, unfortunately, there's not a super specific, okay, I'm going to pick exactly 2. I need to go ahead and use my midterms or max terms for this. So I can actually just build this by, don't forget your brackets, it gives it an order of operations. So I'm going to say, okay, I need A as well as B or C. Or I'm also going to need B and C, all right? So this way I'm collecting at least 2 of all the active bits, okay? That's what this little bit of logic does. Now, that's pretty much all we need for data flow modeling. It is very, very much cool like that. So let's go ahead, copy that over, and just comment it into our structural, because then that will give us how we go ahead and assign this into a structure with wires, okay? So I'll paste it in here, and we're going to that was a little weird. We're going to go ahead and comment these out as just a reference for the logic, all right? And so to determine out, we need to use exactly 1 wire because there are 2 operations here. The number of wires you'll need for certain output is going to be equal to 1 less than the number of functions there, okay? And so, special thing with structural modeling, we're actually calling the gates themselves. So rather than using these fancy symbols we just used for data flow modeling, we'll be using AND, XOR, OR, and NOT gates, okay? So that's the primary difference between these different types of modelings, and let's move forwards. So let's just begin with the out. We go ahead and say, okay, we need a wire, so I'll just say store out 1 is going to be my wire for that, okay? So I can go ahead, perform this. So I call the function XOR. Now I need to label the gate that I've just made. So I'm just going to call that XOR1, okay? And then I need to assign the inputs to that module, okay? So I've called a module called XOR, and it does XOR, okay? That's how it goes. Now, I need to supply where the output goes, which is XOR out 1, and then what I put in, which are A and B, all right? That's a function. That's very happy. Next up, we need to do the final XOR, and it gives me the output. I've already defined my output. So call a second function, call it XOR2. I'm assigning it to the output, and it's just going to be XOR out 1 with C. Okay? Fantastic stuff. We can keep on moving. We go ahead and we look at this little mess over here. Potentially one of the most notable ways that you'll need to break these things down is noting the order of operations, especially indicated by our brackets. So I'm just going to work from the innermost brackets and begin with an OR statement. I'm going to need an output for this. Mind you, there are 1, 2, 3, 4 different operations here. There are 4 operations here. So I'll need to use 3 wires for that. All right? And so I'm going to do an OR out 1 as our first wire. We're going to need a wire for the AND. And out 1. And then we're also going to need an output for this AND over here. So I'll call that AND out 2. All right? And that should be just about all of our wires. So let's go ahead and put this into action. So we call a function OR1, and then we're supplying OR out 1 with the OR of B and C. Next up, we need to perform the AND function. I'll call it AND1 of, I'm going to store it in AND out 1, and it's going to be of A as well as OR out 1. Okay? And then just moving forwards, very much in this mindset, I see another pair of brackets, B and C. So I need to perform a second AND function. It'll be AND out 2. I'm going to be assigning to. Yeah. Exactly. So it's very much mathematical in this sense. We've got to break it down from the innermost set because that's what we need to execute first. And if we were to lay this out in a manner of schematic diagram, then yes, those would be the gates that come first. Right? Thank you very much for that question. Oh, okay. So what is the purpose of the wires, right? Is that like the question? What's the purpose of the wires and what do they do? Yeah. So the wires, if we were to draw a schematic, the wires really go ahead and identify, okay, I'm storing a value in just this. It's not a register. It's just a placeholder variable, okay? So I take my logic in, it runs through the first set of gates, and then there might be a wire coming out of that gate which we need to run into another gate. It's not an input or an output, it's kind of both, okay? So we use it as an output to a gate, but then it's the input for something else, right? So that's the purpose of a wire. All right, so wires, very much how structural modeling actually just like pretty much builds the circuit all together with the gates. A wire is a wire. All right. So that's that. We've gone ahead and implemented almost everything. However, we just have this one last big level OR gate at the end of the diagram. Okay, so we need to perform a second OR function. I'm going to call it OR2, and the output is going to be to the carry, and the inputs are going to be AND2 as well as AND1. Okay, and out 1. And out 2. All right, good stuff. Ooh. Yeah, so assigning wires, the thing is a wire isn't really, it's not really a register, okay? A wire is more of an output to your beginning logic, okay? And then an input into future logic. So it's the way that we compound logic in that sense, all right? So that's referring to our inputs, okay? So we can only directly change our inputs. The wire is a resultant of certain levels of gates, okay? So we have an example on the board. We have A and B and C as the inputs. And then let's say after the very first AND gate, we have that wire there, all right? that wire there, I cannot just say, oh, I'm going to let this be 1. Because I would need to go ahead and actually explain what the inputs would be to make it a 1. Okay? So sometimes it might be too ambiguous to assign that a certain value, because it could mean different input conditions, which changes the rest of the circuit.
Whereas a register you'd be able to.
Register, I'm able to.
Think on a breadboard. If you have just a wire, you can't give that wire a value.
Yeah.
You need to take that wire and plug it into the output of something, and then it has value.
Well, if I do like assign wire equals 1v0, then I just put a ground code.
Well, that's, again, then changing your circuit. That wire is no longer a wire, it's an input. Right? How does that sound? Yeah, no?
Sounds weird, because I can do like assign a wire array something outside and always at 4.
Okay.
I can't do it inside and always at 4.
So the assignment is, let's just think about this from the perspective of the board, right? Pardon? All right. Well, I'll just clarify just for the sake of completeness, and then we'll move on. So the main issue there is just understanding that when we assign wires and everything like that, the equation that we use for them is just a resultant function of previous inputs. Okay? So it's really the wire responds to the inputs. So we can't just drive the output. That's not quite how it works. It's dependent on the beginning. All right. So that is modeling. That's like all 3 of your main modelings. We got our behavioral, you got our data flow, and we got our structural. Okay? They're all different layers of, you could call it abstraction from gates. Okay? Good stuff. So what we're going to do now is go ahead and try and implement different modules into our code. So let's say I wanted to, instead of do all this wiring and whatever, I just wanted to use a previous module I've made. Now you'll note that, oh, I've already used this adder code over here. So if I wanted to go ahead and just have an adder in here, let's say this is a bigger branch of code, I'll actually just create a new source. I'm going to call this the compilation. Next up, finish. So this is going to be a compilation of different modules, okay? So in your lab test, something you may need to do is to go ahead and use multiple modules within the same kind of code. And using this modular thing just stops us from repeating the same code over and over again. You probably would have found this in your assignment, but just for the sake of completeness, we're going to do this. So I can go ahead and assign modules, but let's see what I can do. If I go ahead and call modeling, can I call modeling like this? Not quite. So how do you guys think we would implement, let's say, the structural module that I've just made into this new compilation module? What would we do?
Like how we did the OR gate, so we call our module, then we name it, and then we add it whatever we want.
Fantastic. So I would say structural. I hope I spelt that correctly. Structural, and I'm just going to call it S1. And then let's go ahead and feed it some inputs. So I'm going to need to define input A, input B, input C. I'll worry about outputs now, I guess. And we're just going to go ahead and jump back into structural to see how I've actually structured the inputs and outputs. So I've supplied the 2 outputs first, and then I've supplied the inputs in that order. Okay? We might note that for a full adder, it doesn't really matter what order we put our inputs in, as long as, yes, they're all of the same kind of binary nature, but the out and the carry, they do matter which order we put them in. So, run back over.
There's a way to assign them, right? To assign the,
Sorry, what was that?
Isn't there a way inside of the module to assign whatever we want when we're instantiating it to be that output in particular? For example, if I want something to do that, instead of just doing it based on position, there's one where you can
should be.
The dot notation, is that what you're talking
I
about?
think it is.
Yeah.
The
If we
like dot
create
X.
a new
Yeah.
test fixture,
Yep.
we'll be able to see it show up.
Okay.
Yeah. It is in the text
Sorry for
fixtures.
jumping ahead.
No, that's perfectly fine. We're going to cover text fixtures in a sec, but just for the sake of that, test 1. Moving forwards, we're going to call it compilation. Actually, I'm going to test the structural first. It runs, it makes this, and you'll actually find it's going ahead and it says dot out.
I want to zoom in a bit.
Yeah, let's zoom in a bit so you guys can see. So the dot out, this is identifying, okay, which variable within the structural instantiation am I assigning there? So then it doesn't matter if I read all my things. Thank you very much for bringing that up. So you can do that, 100% for it. What I'm going to do is just try and supply them in order, which is very much how we go ahead and supply it out AND gates in a certain order. So I'm just going to say out 1, carry 1, and then A, C, B, bam, okay? Then I might define the outputs, out 1, and the other output, carry 1, okay? And so this way, I've gone ahead and I've just called the structural implementation, labeled it as a gate called S1, and then supplied it the following inputs, okay? Now, let's go ahead and move on to some test fixtures. All right, so test benches. We go ahead. We've made one for the structural document. It goes ahead. We don't need to worry too much about this, but when we run test fixtures, we're going to assign registers to each of the inputs so we can go ahead and change those with time. And then the outputs are going to be wires. Why is this? Because we are driving the inputs to give us specific outputs, and then we're reading those outputs. We're not directly changing the outputs, okay? We instantiate our unit, and then we're going to begin the test. So just so that we all understand, it's very important to have an initial condition for each of your registers. Otherwise, it's going to throw a fit and say, wait a minute, you are ambiguous, big red line kind of thing. You might have seen that once or twice in your assignment stuff. But next thing is, on the timescale, you'll see that we're on the timescale of 1 nanosecond, okay? And so when we say hash 100, it goes ahead, waits for 100 nanoseconds. This is a nice, just like timing thing, so we can actually observe in the test bench what the output is according to certain inputs. All right? So let's go ahead and do this. So typically, the structure we'll do for this is a always begin. I'll just forever begin. My bad. Forever begin. I'm going to wait 100 seconds every loop I make, and then I'm going to go ahead, say that this kind of binary number indicated by curly brackets, I've strung together A, B, and C, is going to increment, okay? Bam, all right? And now if we were to run this, let's go ahead and see what would happen. So, run.
Now running this one, it's a bit old, so getting it to simulate is funky.
Yes. Just one. Then we need to double click. Yes.
However,
I
the
think
error says syntax error near end module. Can anyone spot what the error is? Anyone see what the error is? On line 60, yep.
Yep. Exactly. Good stuff. So we run it, and now because it's not C. It's all right. So you can see that this has run for ever. Let's try and see what's happened. Pardon? Yep. This one. Yep. There we go. All right. So it was on the scale of picoseconds. My bad. And so we can actually see the logic out of this. So we're driving A, B, and C, which are these lowest three. We know that if we just take a peek, let's not screw that up. 1, 1, and then when we have 2, it pushes it to the carry. We just double check the implementation of this, all right? And it works as expected. Perfect. All right. Now, what might I do if I want to run it for longer than 1,000 nanoseconds? Let's go ahead and see. Other menu.
No, I said at the top right.
Top right.
Small menu.
Yes.
Yeah, that one.
Next one. There we are. My bad. All right. So, in my test bench, I can try and identify how long it can go for. Okay? But we don't really need that. Just if we run this, it'll run until the simulation says, wait a minute, we've done literally everything. So let's go ahead and move on. So I think at this point, I'm going to hand over to Sudarshan. At a later point in time, we'll cover mux and decoder, and then we'll move on to the stuff. So, any questions?
Which bit designates which element will be displayed?
Oh, okay. So, because we've identified the wires and the registers, those are what it is seeing. Okay, so that's what we're looking at within the simulation. Okay, it should. There were 3 inputs and 2 outputs. There were 5. Yeah. Yep.
You can see ABC, out and carry.
Yeah. All good.
No, the volume's great. I checked. I'll leave it back up.
Yes, what's up? Yes. No, style is not a consideration for this exam. It's
As long as it works.
Demos won't bother too much with debugging your code. If you get some wacky error, they'll try and help out, but
Debatable.
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 It's like more of, oh, has anyone seen this error before? If we all haven't, we know who's coming from then. So, okay, that's up to you to debug.
Strictly speaking, there's no debugging from the demos in the lab exam.
Yeah.
Okay. Can you hear me well? Cool beans. All right. So we went through earlier, there was a question about assign statements and wires, etc., etc. You'll notice that we have a couple ways of generally assigning things in Verilog. You saw that we can do, if we have a wire X, we can do assign. We need inputs first. Let's give it an input A, an input B, and an output Y. We have a wire X. We can say assign X equals A and B. And what this does, it assigns X to the output of A and B. You can also have something called buses. Not as in the transport mode, but a bus is a collection of several variables in one name, kind of like an array in C, if anyone knows that. Way we can do that, we can declare an input bus or array or vector, however you want to call it. Let's say this input has 5:0. Does anyone know what this funny syntax means? 6 bits, perfectly. And why is it 6? I only see the number 5 there.
0, 2, 5, 6.
Perfect. So we can take in an input of a 6-bit array where the most significant bit is 5, the least significant bit is 0, and we can say that the output is also a, let's say, 6-bit array from MSB 5 to 0. What we can do then is we can assign, let's say we want to assign, this could be a good use in LEDs and switches. If you have on your FPGA, you have, I think, 12 different switches and 12 different LEDs. If you take them in as inputs and you want to assign each switch to each LED, what you can do is you can say assign Y0 equals A0. What this does is it takes in, is that zoomed in enough? Yeah? Oh, good. It takes in the 0th bit of A and assigns it to the 0th bit of Y. Another thing we can do is if you want to just equate the entire thing, you can say assign Y equals A. And what this does is it takes in everything in Y, everything in A, sorry, and puts it into everything in Y. This only works if the length of the vectors match. And another thing you can do is if you want just a few of them, you can select portions of vectors like this. So if you have your 5 to 0 bit Y output, you can, and you only want, say, the last 3 bits, what you can do is 2 to 0 equals A 2 to 0. What this does is it takes the last 3 bits of the A vector and assigns it to the last 3 bits of the Y vector. If you want to be funny, you can also do this. Functionally, it just shifts it one over. So these are 3 ways of indexing arrays or accessing elements of vectors. I think you should never call it an array. People who like Verilog will get very, very angry at you. And so we have wires. Someone also asked, what is a reg? We can say reg Z. If I try to do assign Z equals A and B, I should get a lovely error when I try to compile this. What you should do instead, so a wire, like we said, is kind of an output of a gate or an output of a module. It can store values for you to use it later, but you can't directly give it a value. It's kind of an intermediary between 2 inputs and outputs. What a reg is a reg is like a variable. Like in C, it's a normal variable. What you can do with the reg is you can give it any arbitrary value. You can, if I had a nice 16-bit variable, I could give Z a nice value of that would work. This syntax might look a bit funny. What this does is it says it's a 16-bit number, and I'm giving the number in decimal format, D for decimal, and there's the number. I can also do 16B and then give it a bunch of binary, or I believe the other one is 16X, and I can give it like 6FA. Cool. However, if I try to do this, and I hit save, we get a lovely little error here. Line 27, syntax error near the equal sign. Any idea why? So with regs, they are a kind, well, with wires when they're placed on the board, the reason they can't hold any arbitrary value is because once they're placed on the FPGA, which is like a breadboard, they can't move, they can't change. A reg, you're assigning it some arbitrary value, and you're going to be manipulating that value at any point in time. So it can't physically connect any wires and have them move around. Because what the FPGA does, when you run your implementation, synthesis, generate bitstream, all that, is it basically tells the FPGA what gates to put down in the FPGA, what wires to connect between these gates, and how to interact them with your outputs. Therefore, this is illegal. what we do instead is something called an always at block. We saw this in the first example of your behavioral modeling. So what the always at block does, always at, we can do a begin, we can do an end, and now we can say z equals 16d semicolon. There we go. There was an error before I put this asterisk in. That's a good point. Inside these, when you say always at, it checks every time something within here changes, this code executes. So that's why this kind of works. When you do always at star, it says whenever the FPGA decides to just update whenever, give Z this value. Give Z dynamically this value. If I had an input clock, I could say be sensitive on the clock. Whenever the clock changes, I can give Z this value. Or I can give Z the inverse of what it already was. What I can also do is, if you want just the positive edge of the clock, you'll recall that a clock signal is like that. Right, and this is the positive edge, because it's going from low to high. You can trigger on the positive edge of a clock by saying pos edge, always at, brackets, pos edge of the clock. You can see it's nice and blue because it's a good word. Pos edge of clock, when that happens, flip the value of Z. You can also have neg edge of clock. When the negative edge of the clock happens, flip the value of Z. You can have neg edge of clock and pos edge of clock. Whenever that's basically whenever any bit of the clock changes, flip the value. That's, sorry, typo there, pos edge. This is also not valid code. Let's comment this out. You'll see that this happens, this is basically a long way of saying whenever the clock changes. So what you can just do instead is just say CLK. And what this does is whenever this value changes, then update the inside. If you want to do it whenever anything changes, you can do a good old star, asterisk. You don't even need the bracket. You can just do always at star begin, and it flips the value. This would actually give an infinite loop. So you shouldn't actually flip a value infinitely, but you can give it 1B0. A good value question.
Does the asterisk, like, does a block only execute when anything inside the block changes? Because one of my demos told me that like any variable, like you got Z there, right? If you had another variable outside, so say clock changes, the block won't execute. Is what I
Potentially. I'm not too sure. Potentially.
We were told it's for like combinational logic, so that whenever something executes, then it
That's what I'm aware of. But that might also be the case, I'm not too sure. So those are your different ways of triggering an always at block. And you can, so on the board, we said that wires can be connected to AND gates and OR gates, etc. With a register, there's no real basic circuit gate that can hold value, that has any memory. Does anyone know what new circuit element that we have can remember things? Is a memory module? Flip-flops. Flip-flops can remember things. They have a input data, and they can have an input clock signal, and what they do is they remember stuff until the clock signal changes. So therefore, whenever you have a register on your board, when it creates all the little gates on your board, it makes a flip-flop on that board to store this value. If you have a 16-bit Z register, you would have 16 flip-flops connected on the board that store your Z value, and you assign them different values whenever it changes. Whereas a wire is a literal wire, and a like between say a NOT gate and an AND gate, and it contains intermediary output. Okay, now let's make a flip-flop. We said that reg is a flip-flop. How about we make a flip-flop? if you look at a flip-flop's actual implementation, this is a latch. A flip-flop is actually two latches chained together. But if we tried to make this, this would be a big pain, right? You would have to say, you would have to make a wire here. You'd have to make, let me make that bigger, sorry. You'd have to make a wire for this, you have to make a wire for that, you have to connect these wires up, you have to place down 4 different NAND gates, manage all the inputs. That's a pain in the backside. Therefore, we can rule out structural modeling and we can rule out data flow modeling because we really don't want to be bothered with all the implementation details of this. Instead, what we can do is we can use our very brand new, lovely best friend of a always at block. Let's call this a D flip-flop. We'll want an input of the data. We'll want an input of the clock. We'll want an output of Q. You can have an output of like the inverse of Q bar. Let's do it anyway. Strictly speaking, you don't really need this. You only need the Q bar output when you're actually making it in a circuit because it feeds back. When we're making it in our thing, we don't really need it, but it doesn't hurt. Let's hit save. Let me make this nice and big. Cool. So inside a D flip-flop, what's the basic function of a D flip-flop? How does it actually function? Any ideas? What's its purpose in life? Perfect. So in case you couldn't hear, the answer is a D flip-flop takes in the data in D whenever the clock input changes. Whenever the instant that the clock input changes, it takes in the data and remembers it and outputs it until the clock changes again for the next time. Let's make this a positive edge triggered flip-flop. Like we said, you can have a positive edge and a negative edge. Right? We can have it triggered on the positive edge or triggered on the negative edge. Let's make this a positive edge. So we do an always at on the positive edge of the clock. Do a begin, do an end. What do we want to do whenever the clock changes? So how do you remember it? How do you think we shall code this up? That's a good point. Where shall I put reg? Start here? Inside here? Reg? Any ideas? Like that? Here? Reg? Like that? Sure, you can have reg state. Alternatively, so in our flip-flop, like we said, the Q is the output, right? So we can just make Q a reg. We can make Q bar a reg. That way we can directly set its value. We can say, whenever the positive edge of the clock happens, what we want to do is we want Q to equal D. That's it. One line flip-flop implementation. Strictly speaking, question? You're right, you're right. Q bar equals not D. Yay. Okay, strictly speaking, this works. However, flip-flops they work kind of different in terms of time compared to your normal gates, right? So we have an equal sign, which what it does is it kind of interrupts the flow of your code, assigns it the value of Q to D, and then keeps going. What we also have in Verilog is called that. What this does is it doesn't actually interrupt the flow of your code. It kind of connects a pseudo wire between Q and D to save the value and lets the other code keep going. You will use this heavily in your timer implementation in the coming lab if you haven't done it already. So just for completeness, we'll have it like that. And you'll notice that while this will all work fine and dandy, the output of Q is undefined initially. Q actually has no beginning value until the positive edge of the clock happens. This isn't really a problem in your breadboards, but when you do it in an FPGA, we tend to like to have all our values defined at all times. If you don't have it defined, you'll see in a simulation, have you ever seen like a blue line or a red line with like Z or X because it doesn't know what's going on? What we can do instead is we can just have a nice default value right there. We can just give Q a default value of 0, and then everything else goes on as normal. It's a very fun little piece of trivia. You're right, you're right. I really like, I would just like to do that, like delete Q bar, but keep it there anyway. All right, and now we want a question. It's called the non-blocking assignment operator, whereas the normal equals is the blocking assignment operator. It blocks the flow of your code until that assigns and keeps going, whereas this kind of just happens on the side. It means that if we have a whole bunch of registers getting set at the same time, they'll happen in parallel at the same time. Whereas if we have this, and it blocks the flow of the code, and then the value of D changes, then Q bar will take the different value of D, and Q will have a different value of D if D changed between that nanosecond of that code. Whereas if you have 1 second, if you have this, these both execute at the same time. Mm-hmm.
So that's sort of the different, kind of like a serial shift register and parallel shift register. Could also like difference between those two would be something like that. Because one, it's like one at a time. Right?
Mm-hmm.
Whereas
Yeah, sure.
it's all at the same time.
Pretty much, yeah.
Right.
So this happens, this lets it happen, and they all happen at the same time, whereas this happens first, and then this happens. So if D changed, if in this half microsecond, half nanosecond value of D changed, then Q bar will be taking a different value of D if we had just a normal equal sign. Does that make sense? Awesome. So just for completeness, we do that. Cool. Also, if you did this, it would take like half a nanosecond extra time. If we're on like a really time optimization and we want this to happen in as little nanoseconds as possible, having that execute first and then this execute costs us that extra precious nanosecond. If that was a concern for you, this is a concern in high frequency trading. And the existence of this parallel operator is why FPGAs are used so extensively in high frequency trading or in any application where speed is of a really big concern, because it can execute infinite things in parallel at the same time, whereas your computer, it really can only think in one direction. Okay. And now we'd want to simulate this. We want to make sure that it actually works, right? Give this that. What we can do is we can create a good old test bench, test dflop. Was there a question? No. Test dflop. Nice and big. We have a D and a clock, a Q and a Q bar. This is the syntax that you pointed out earlier. We can instantiate, a module based on different words. If we had, this is the actual name in the dflop module, and this is our name for it. So if we had banana, they could just call this banana. Awesome. I should probably put that back just for clarity. Yes?
Well, like, well, that's when you change it, like, because actually, like, the one with like the dot D, that first D was actually the old function we created. But that changed that name.
Yes. So this is based on the names we give it here. So like D clock, Q and Q bar. So this stuff needs to match, and then this can be whatever name we have in here. Cool. Let's just call it D just for clarity for now. And to simulate our D flip-flop, what we'll want to do, we have given D and 0 a nice default value. We can wait 100 nanoseconds. What we can do is, we made this a positive edge clock or a negative edge? It was positive indeed. What we can do is we can set clock to 1 now. Clock has gone high. We can wait another 100 nanoseconds. We can get D equals 1. What should happen now is that the D flip-flop should not save this output. Whoa. Sorry. So we waited a bit and the clock turned high. Waited a bit more. We can set the clock back to low. And then when we set D high, the flip-flop should not take our value because this was a negative edge. The clock went from high down to low, so the D flip-flop does not store our value. What we should do now is if you wait another 100, and then we set the clock back to high, at this point in time, when the clock climbs back up, the flip-flop should save the value of D, which is 1, and send it in the output. All right, if we run the sim, what's that doing? Simulate. I want to save high 1, why not? Sorry. This is our output. So we start off with Q is 0, Q bar is 1, as expected. They should always be the opposite of each other. And then, after 100 time, the clock goes up to high. After another 100 time, D goes up to high and clock goes down to low. We note that this is a negative edge, so the D flip-flop does not remember that value. It is still low at that time. And then what have I done? And then when the clock goes back up to high, that's our positive edge. Therefore, the flip-flop remembers our high value. Is that clear? Make sense? Awesome. That's our flip-flop. Well, you saw me. What do you mean? No, you saw me code it up right now.
When you made the file itself.
You saw me type everything in. What do you mean?
Just compliment your typing skills.
Yeah? Oh! Oh, does this not come for you when you make a test bench? Really? Well, that sucks. Well, in that case, I'll go through the syntax briefly. Well, in this old software, which is clearly, for some reason, better, when I hit create a new test bench, it gave me all like the basic boilerplate code, because it's going to be the same every time, right? So what we'll do is we'll declare our inputs. These inputs will be regs, because like we saw here, we are assigning these arbitrary values. So these are going to be regs. Our outputs can be wires here because they are being driven by the D flip-flop. So the D flip-flop deals with all that. The output inside our test bench is just a pure wire. Yeah. Unless, in a test bench, yes, because you should never really want to modify your output directly, right? Yeah, you're testing for the output. If you mess up the output, what are you testing? And then we have our D flop. That's the name of the module that I gave here. D flop. We call it UUT by default. You can call this bananas again. It doesn't really matter. This is the name that matters. It's the name of your module. This is what you want to call your unit under test. If you are testing two separate D flip-flops, these would have to be different names, right? If you just had UUT and UUT, this would mess things up real bad. So you would need like UUT2, or you could have apples and bananas. Up to you. Bananas. So that's your unit under test. That's what you're testing. And then you do an initial begin. And then we type all that. We hit end module. A quick thing to note about initial begin, or in Otto's test, you saw that he did a forever begin, wait 100, let's say flip the clock, clock equals clock end. This would be useful, actually. If we move this, we just let this run in the background forever, and then we can ignore toggling our clock here. Well, we can have another minus 100 wait. Ignore that, we can just play with our data. This is good to simulate a clock. The thing to note about initial and forever is that you cannot use these inside your actual Verilog code. Initial, begin, the hashtag delay, anything that is really time dependent cannot be synthesized in your real code. They are only allowed in your test benches. This is because FPGAs by themselves have no real concept of time, right? Like our computer has a concept of time. The FPGA has no bloody clue what time is. Your simulation has an idea, but the FPGA doesn't. So when we're writing our code, we can use always at blocks. We can use our clock to kind of give it a vague idea of what the time is, but the actual timing does not exist in your actual code, only in your test bench. Cool? Awesome. Another quick things about Verilog. You can have if statements, you can have else statements. So we can do if, we can do this really jank, always at on the clock. If clock equals, let's make a latch now actually. So we can do if clock equals 1, then we can say Q equals D. Comment this out. This is no longer a flip-flop, by the way. Let me just latch. I can spell. And then else, begin, well, nothing really. Else, begin, Q equals Q, right? Nothing changes. Oh my God. Else, begin. End. There we go. They're sure to be in brackets. Clock double equals 1. Okay, I love syntax. Yep, it's just a standard if-else statement. There we go. This is our always at begin, end, else, begin. The syntax error on this near line 38. Oh, semicolon. There we go. And this is our flip-flop because we messed with it. Okay, so we can do if statements. We can also have something called switch case statements. What we can do is if we had an input big bus, which was say, let's make it 3 bits just for ease. Input 3 to 0 of big bus. Sorry, 4 bits. We can switch on the input. What we can do is do something called switch, case, big bus, and we can say that if big bus equals 4 bits, we can go up to 16, let's say, thank you. If it's 4D12, then we can do something with the number 12. Otherwise, if it's 4DH, do something else. Otherwise, let's say we like these values, right? We can say Q equals 1. Or if it's 4D8, we can also say Q equals 1. Otherwise, every other value, we should make the output 0. If our input of big bus is 12 and 8, then our output is 1. Otherwise, our output should be 0. So we can say default, Q equals 0, and then we just do a good old end case. Enter, give this a good tab, just for clarity. Does this make sense? This is like a big, this is just like a big if statement glorified in nice readable syntax. What this does is it takes in the value of big bus. If it's 12, then it executes this, or if it's 8, then and it executes. Let's say if it's 8, then we flip the value of q. Otherwise, you make it 0.
So per case of whatever do that.
Yes. Yes. And only that executes. Cool. Also, one final thing with our always at begin and end. With any statement in Verilog, if it's a begin and an end, and you have only one line inside that block, you can skip the begin and end altogether, and you can just do that. Right? If there's only one line of code that is executing inside that block, you can skip the begin and end and just write it right there. Awesome. With that, let's try making a mux and a decoder, this time much faster than you hopefully did in Lab 3. Otto, want to make a mux?
Let's do this.
Mux. Close deflop. Close. Actually, I might make a new project to avoid our old syntax errors. Mux.
All right.
I don't know. Project, new source, Verilog module, Mux. There you go.
Nice. All right.
Take it away.
All right. So, I'm just going to show a couple ways to make a mux, because there are some silly ways, there are some like smarter ways, and so, I mean, let's begin with a silly way. Okay, let's general silly way. Usually muxes we're going to use like, actually just going to hop onto Edge and just like show you the general mux.
Yeah,
Multiplexer, 4 to 1. Jeez, I cannot type. Just the logic, okay? And it looks something pretty horrendous, okay? There's a bunch of ands with nots, and you have your controls A and B, and then the inputs to your mux over there. So we don't really want to integrate it as a data flow or structural model. We just want to use behavioral. Okay, so let's hop back over here. We have mux over here. I'm actually going to make a new project. I'm going to call it silly mux. Okay, why am I going to call it that? Because it's probably what a lot of people are going to do in their lab exams if they need to make one. And so typically we define our inputs and our selections. So input, yes, zoom in. So inputs, we're going 4 to 1. So I'm going to make 4 inputs over here. Just going to call these my in. Yeah. And then I'm also going to have my inputs as the selectors. Okay, so I'm only going to need 2 selectors because 2 to the power of 2 is 4. Okay. Selectors. All right. So the reason I noted that, okay, I need 2 selectors for 4 inputs to my mux is because the selectors generate the binary selection of each of the inputs over here. So I have 4 inputs. I need to have 4 numbers expressed in binary. I can do that with 2 bits. Okay, that's just the general gist of how that goes. And so we love behavioral. Let's go ahead and perform it. So always at, we want to do this at the case changes of our selector. Okay, so actually, not necessarily, not just the selector, because you can imagine if your selector is active on a certain channel of your multiplexer, we also want it to update what's going on if that specific channel to your multiplexer alters. Okay, so what I'm getting at is if I just went selector, I need to begin. Exactly, so the input line could change. So I'm just gonna go ahead and work this through. We do a case by case on the selector value. we begin with 2-bit binary numbers. Doing this all over again. I need to define an output, so output out works. Make sure I use commas here, not silly semicolons. Out equals in 0. And then we just move forwards with this. And I do Control D. Thank you. So that was just Control D, duplicate. It will be helpful if you need to make a silly mux. But this is how we would go about just implementing general mux. We have only used the selector. Now, as we've mentioned, if I were to run this code, it says, okay, as long as I change my selector, then I update what is the output to this silly mux. And that is awfully silly, because if my input changes, my output to the mux should also change, right? So I should also have this always at block triggering on the input, okay, as well as the selector, okay? So, what have I forgotten here? End case, all right? Ends are very important just to let the program know that, okay, I'm considering this block of code for this action, all right? Bam, bam, bam. Here is our silly mux. I'm going to save that. Now, why did I call this silly? Does anyone have any ideas? Perfectly fine if you have no clue. The reason I called it silly, actually, let me just go ahead and copy all this code into the general mux. The reason I called it silly was purely the fact that it's so many lines. It's like 6 lines. It's so many. You could do this in a lot less, okay? And quite generally, the way that we want to be smart about this is this does take some time, okay? This, writing it out in your lab exam, takes time. So if we think about it, this binary that we've used as our key, the input reference in our array is going to be the exact same as that number in binary. How about we just chop out the middleman and just assign it as such? We can just say, okay, let's just say out is going to be equal to in cell. Right? How'd that go? Because then my cell, a 2-bit number, gives me a reference for my input, which I can then assign to my output, okay? So, does this work? What do we think? It has essentially done the exact same thing as the silly mux, okay? So both of these should perform the exact same, all right? That is a mux, that is a multiplexer. If you wanted to increase the size of your multiplexer, you could always, let's say I want to go 8 to 1, 8 inputs to 1 output. I'll go ahead and push this higher. Let's try and figure out how many selector beams I would need. 8 numbers, binary, that's 3 bits. I need a total of 3 selectors, all right? What's up?
I've seen the beginning of syntax there saying procedural assignment and don't register out is not permitted.
So we've said out over here. Now, we've said procedural assignment. We don't like using this. So, reg. Fantastic. And then, do you reckon we have the same issues with this kind of mux? Because we will. In any case where we need to assign an output via this method, we always need to use a register, okay? This is probably the main drawback of going ahead and describing it behaviorally. You need to define things using registers rather than just saying, oh yeah, I combine this logic to give me this thing, which can be for better or for worse, definitely in terms of implementation. But it does its thing.
In the scope of this course, strictly speaking, describing it behaviorally should be fine, unless they tell you not to. But if you're doing this for like a real implementation, and you are concerned about the speed of your circuit, going to be expensive. Whereas if you use a structural modeling of just like AND gates and OR gates and NOT gates, that will happen almost instantaneously, and it's much easier, much cheaper in terms of the amount of gates you have available on your FPGA.
Yes. Just for the online viewers and for future viewers, to reiterate what Sudarshan said, registers, flip-flops, they are expensive both like in the circuit as well as time-wise, okay? We like having things operate instantly, which this takes bonus implementation. But for your course, behavioral is perfectly fine, unless they ask you not to. Hop onto decoder or question one?
Question one.
Yeah, let's go ahead and push onto question one of your sample paper.
Laughing sound.
So,
Let me grab that up.
yeah, let's go ahead and grab that.
Let's go and we'll be right back. Some downloads, I swear. You're all looking at my downloads, eh? Oh,
I mean,
I'll find it.
could try and grab it off of the content slide.
I love to be right back. I'm so bad.
You did it really well.
While we wait, what are everyone's thoughts about the lab exam? Is there one today? No, next week. Right?
Next
week. Is everyone sorry. Is everyone good, bad, prepared, not prepared, bad? So far, do you think you've improved or you remember extra things? Has this been helpful?
Yeah.
Yay! Cool.
That's what we expected.
There we go.
All right.
This is the sample lab exam that's been running as a sample lab exam for the past, I think, 6 years.
It really has been.
Question 2 is new though.
Question 2 is a little new. So I believe we're covering 2 different question 2s if we have time. So let's go ahead and hammer this out. So here we have question 1 example. What's up?
What we'll do is we'll freeze the screens so
You
that,
can freeze one of the screens,
Yeah.
potentially.
because the bubbles inside here are really hard to see when zoomed out.
That's true.
There we go.
Bam. There we go. All right. So we can note that we have quite a few interesting things with this circuit. Let's just figure out what we need to do. So we need to implement Verilog HDL code. I mean, that is any type of modeling, so we don't really need to mind with that. Do a test fixture, and then simulate the outputs to fill in this table, okay? It's half the marks of the thing, so this is likely, I'll put this pretty firmly, likely the easy part of your lab exam, okay? So if you can get anything down in like whatever little time you need to cram, this is probably the one. So we see number of gates, be mindful of their bubbles. Bubble means not, so you need to make sure that you implement the knots where applicable. So let's go ahead and actually just throw this straight into here. Now, mind you, they said Verilog HDL. That probably means not schematic, okay? If they wanted you to draw this and then simulate it, they would ask you to. They probably don't want you to do that unless they explicitly tell you to. So let's go ahead. We're going to go ahead and make a new project. Sorry, not new project, new source, Verilog module. And it's going to be sample Q1, okay? Bam, bam, finish. So I'll just mention to anyone online, please take a little snapshot of whatever circuit that was. You should have access to it on your own Moodle page. In person, we can see it over there, and we're going to be working off of that. So, the number of inputs we have 3 inputs, and we need to double check if they have specific names. So, let's go ahead, double check over here, x1, x2, x3. So, we can just label it as such. Input x1, input x2. Oops.
How we just input x1 to x3?
You could.
You do that for the output?
Could. And then we have 2 outputs,
F1.
F1 and F2. All right. So now we need to go ahead and implement these gates. So I'm looking at gates. And the easiest way in my mind to just, I want to get this done quickly because time is a pressure inside the exam, I really just want to use data flow. Okay, a structural, I need to list out every single gate and every single input, and I need to do it for multiple things. I don't like that. You guys don't like that. Please just use like data flow. It's so quick. You just use single symbols. That's the one. So I go ahead and I look at that, and I mean I can still use wires. I can see 3 wires there, so I can say wire W1, W2, W3. And then I can go ahead. So I'm labeling 3 wires to be the wires that come out of the first level gates. Okay, so I've indicated levels of gates. What I'm referring to is I have this first layer of gates that take certain nots or affirmatives of x0, x1, and x2 and give me these 3 wires over here between the gates. Okay, so let's go ahead and work with that. Wire 1 is the output to the first gate. First gate is an OR gate because it is curly. So we need to go ahead and say assign wire 1 to be equal to, it is a OR implementation of all of these. So it is first and foremost going to be x0, or I'm going to take the negation of x1, and then I'm going to take the affirmative of x2. All right, bam, that's first wire.
You called it 0, 1, and 2. We used 1, 2, and 3 in the declaration.
Oh, whoops. Thank you very much for pointing that out. All right. X1, 2, 3. Okay, so assign.
Sorry, just a question.
Yes, what's up?
Why can't we use plus?
So plus instead of or. The thing is now we're looking at, okay, so typically in like general binary logic, we like to define ors as pluses, ands as multiplications, and that just helps us push binary logic. However, if we're working in a program, plus can mean plus. So you could accidentally go and say, oh, I'm actually adding together these 2 bits, when I don't really want to, okay? It might have unforeseen, like, outcomes.
We're being introduced by like plus minus stuff.
Yeah, so
If you're ever asked to make like an adder program in Verilog, you can literally just do output equals A plus B and that works.
yeah,
You do not need to go through all the hassle of all the individual gates and carries, etc.
unless they specifically
Unless
ask
they
you to.
say for some reason you have to. Like,
So, second wire, second gate. Let's keep it moving. We got the negation of first and second, affirmative of the third, and it is an AND gate. So we're actually just going to go ahead and say, put everything in brackets. We take tilde x1 as well as tilde x2 as well as x3. Okay, bam. Now, something to note is that previously I mentioned that brackets are very important. You'll notice that, oh, why didn't I put a bracket around like these 2 terms? Quite frankly, ors and ands are distributive, so, sorry, it's not distributive, commutative. What's up? There is a bubble at the end of the end. So, we might go ahead and take that into account at the end, or we could take it into account right now. But, very good point. Let's go ahead and do it right now, because it is a function of the gate. Good stuff. So we just take everything and we do that. Alternatively, you could use demoivres, but like, no one really cares about that. Just do it as you've been told. So we move on to the third wire. We have affirmative of the first and last. Sorry, negation of first and last, and it is an AND gate. So once again, tilde x1 and x2 and tilde x3. Bam. All right. So there we have our wires, and then we can implement them to go ahead and find F0 and F. Sorry, I mean F1 and F2. So we have a NOR gate. It's a NOR gate. Pardon? Is it a NOR gate? this one. So it has a line behind it. What type of gate is it?
No, XOR is that one.
Yeah,
This
it's
is a
XOR.
one.
Yeah, yeah.
no.
The top one's XOR. So line behind an OR means that it is an XOR gate. So if we remember the very cool thinking thing we did previously, XOR is given by this little hat symbol, the power symbol. So we can go ahead and just do that between wire 1 and wire 2. So wire 1 XOR wire 2. Fantastic. Next up, we can assign F2 to then be the NOR of wire 2 and wire 3. Okay? So NOR, really we just want to NOT the output of the OR, so we begin with a tilde, wire 2, or wire 3. Bam. And therefore we have all our logic there. Very happy. That's a nice 20 marks. Let's go ahead and make the test bench. So we've saved it. We go new source, test fixture, test 1, Q1. Bam. It's going to be for the sample question. We generate it. And then for you guys, you identify, yes, we have 3 inputs. Yes, we have 2 outputs. Yes, this is the thing we're instantiating. And then let's begin the testing, okay? So we zoom in and let's begin. So we're beginning typically, if we just double check the table of values, usually it'll just be a binary addition. So 000, 001, 010, la-di-da onwards. So we just want to add numbers binarily, which, I mean, if in case you guys forgot, we always go forever begin. We tab it, and then we increment, okay? x1, x2, x3 equals x1, x2, x3 plus 1. Bam. I forgot the equal sign. And then end. So this iterates through each of the conditions, and we can just run it. So
a quick note on the syntax, and I'll say it here next to the mic as well. But you'll see here the curly brackets. The curly brackets are treating x1, x2, and x3 as a single number with individual bits, or like a vector. And what we're doing is that we're saying that vector equals that same vector plus 1. And the plus 1 is a normal addition. It's not an OR, it's just a normal addition. So this is, yeah, it's basically a 3-bit vector with those digits, and it's adding 1 to them every single loop time.
exactly. So it is important that we use curly brackets there, just so it indicates that, yes, we're pushing these together to be a 3-digit binary number, okay? Plus 1, which is just the increment, which tells the program how we want to count, okay? So we've done that. We can then save, select the
Simulation.
Yep. Got it.
Yeah, simulation.
Yep, there we are. There we are. There we are. All right. So make sure you find your simulation tag. Otherwise,
There's an error.
Ooh. Okay. X2 not declared.
Verilog is case sensitive. If you look at your
Oh, no.
Q1 Verilog module, your actual implementation,
Yeah.
you had a capital X.
Let's think about this. Oh my gosh. There it is. Little silly. All right.
Just remember. It's bracelet education.
In true lab demo fashion. All right. Don't forget to zoom to fit. And let's see how that goes. So we got x1, x2, and x3. It is incrementing by x3, which is what we want until x2, x1. And so when we double check our table from the question, which is just over here, we want to make sure that we're incrementing from the correct input first, okay? So I've relabeled these as x1, x2, and x3. That's just because I felt like it. But we can note that, okay, x2 that we have over here, we want that to be incrementing first. We want to make sure that what's incrementing is what's in our simulation, okay? So a common mistake might be that you increment from x0 first. Now this all depends on your assignment of your addition, okay? So I've indicated x3 is the least significant bit. and therefore when I increment, that's what flips to the first, okay? So that's the main thing I want to point out here, and that's why when I jump over to my simulation tab, down the bottom, one of them, there we go. It goes ahead and pushes x3 first, then x2, and then x1, okay, which is what is desired from the question. So bouncing back, I can go ahead and identify, okay, for f0, I get 0, 1, 1, all the way down to the last one being 1. So 0, 1, 1, 0, 0, 0, 0, 0, 1. And then double checking again, I can check f2, and that gives me a, wait, sorry, never mind, 0, 1, 1, 0, the rest of them. Just remember, I'm only performing 8 different sets of initial conditions because I've got 3 bits. So my simulation really just ends at the 800 nanoseconds. So this is what I'm looking at. There's only a 1 on f0 for the second and third condition. For f2 though, it's only on the second condition, okay? So my graph would look something of the sort. Let me just hop back over to the code. Yellow arrow. That's the one. Been a little while. All right. And so I'll actually just indicate it over here. Gives f0, has an output of 0, 1, 1, 0, 1, 2, 3, 4. And then an output of f1 as 0, 1, 0, 0, 0, 0, 0, 0. All right. So that's question 1. We've implemented it. We've filled out the table. We're very happy. That's half the exam. Okay? Good stuff. I'm going to hand back over to Sudarshan. And yeah, here's where the more difficult part comes. Okay?
I hope the mic, is the mic good enough? I have a loud enough voice, I'm sure it's good. Okay, one final note with this test bench that we created, there is a cool feature in your simulator, works on your one as well. If you select several variables like that, and they're all kind of linked together, you know, they're incrementing in tandem, what you can do is you can create a new virtual bus. It treats it like a bus, and you just see there, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, etc., etc. That makes it really easy for you to match up exactly what inputs you need to your outputs. I'll do it again? Okay. There we go. I select which ones I want to select, x1, x2, and x3. I right-click. I hit New Virtual Bus. Okay, it treats it as a bus. Like we said, a bus is a vector of multiple numbers combined together. This will make your simulations much nicer, much prettier. If you so wanted to do so, I'm aware of time, but just a quick extra. If you hit on radix, you can set it to unsigned decimal, and you can see 0, 1, 2, 3, 4, 5, 6, 7, 8. It treats it as a normal number. Anyway, bonus factor side. Don't save. We will now start question 2. This will take you the longest amount of time. What? There we go. Okay, project, new source, Verilog module, question 2. Hit finish, make it bigger. Let me pull up question 2 for you. Create an LED sweep effect. Use LED 0 through to LED 15 to display the output. Only one LED should be active at any one time. This should move from the right to the left, activating one LED at a time. So it performs a nice sweep across all the LEDs. Once you're at the leftmost LED, it should remain on indefinitely. A push button is used to reset, etc., etc. The code, 20 marks is for your code, 10 marks for your constraints file, and 20 marks for the implementation. Constraints file, before we get all this started, you'll notice under your lab exam on Moodle, there are some provided modules. In your lab exam, you get given these modules inside here. Please use them. We're going to use them right now. I'm not bothered to make an entire timer myself. What we can do is we can use these modules. They also have a master XDC file. If you look at this, it's all those annoying things that you had to type out for every constraint is already here. LED 0, LED 1, etc. It's already mapped. So these 10 marks, if they still give you those 10 marks, are the second freest marks you can get. All you have to do is copy what's in here into your actual file and comment it out. Make sense? That's the constraints file. The other stuff we provided is a shift register, a timer, and a basic template for a finite state machine. This is what you're given in Lab 7 as well. A finite state machine is a bunch of theory. We don't have time in the next 15 minutes. Anyway, if we look here, there's a timer provided. We'll notice here that there is a kind of time element involved inside our code here. The full sweep should take 2 seconds, i.e. each LED is for 125 nanoseconds. So what we want to do is use this timer module which pulses the output high for 1 clock cycle every number of clock cycles. We'll use this if, I forget the exact clock frequency, but if a clock cycle was 1 nanosecond, then you would use 125,000 here as your duration, and this would pulse high every time that threshold is reached. More on this in Lab 7. So if we copy this, we just absolutely shamelessly steal this code. Timer.
Thank you for your time.
No worries. Steal this, save it there. So just reiterating, it takes in an input clock signal, which is provided on your board. The board has a built-in clock frequency, which you'll learn in Lab 7. You take in a reset pin, and then every time, every clock cycle, it counts up by 1. It counts up until it reaches this duration number. Once it reaches this duration number, it will send match to be high for that 1 clock cycle. Way we can implement this now is we saw that we had a 16 LEDs, was it? LED 0 to 15. So we'll want an output of output reg from 15 to 0 of LED. This is a common mistake that I almost just made. When you're indexing your vectors in your code, you would do stuff like LED 0, right? However, when declaring it, you declare the size before the name. Keep this in mind. If you do this, it will not work. We get lovely little syntax errors. Okay? This is a very common issue. Save. And then we have an input clock signal. What else do we have? We say a push button should be used to reset the sweep and start again. So we'll take that as a input. So what we would do in our constraints file is map the reset. We look here. We would map the reset to one of these push buttons. A push button is provided. Switch LED segment. No push button? Am I missing a push button? Potentially. Oh, there we go. Button center up, left, down, right. So we'll pick one of these push buttons. We would map them to our reset. Our clock is provided here. Get ports clock. So the clock is at a period of 10 nanoseconds, I believe. And then what do we want to display? We wanted to display the LEDs, which are all these LEDs here. We would copy that into our constraints file. Exit, save. So now what we want to do is we have the timer. We will do the calculation. We said it was 10 nanoseconds per period. We want it to stay illuminated for 125 milliseconds. So if we do a good old 125 milliseconds over 10 nanoseconds, we get, what's that? It's a large number. So this would be our duration. When we call our timer, we can do timer T1, Like we saw, timer is the name of this module. T1 is the name that we give it. We can call it bananas, does not matter. The timer takes in an input of clock, reset, duration, and match. So our clock is just the clock, reset is just the reset. Duration, we said was that big number. What size did it want? It wanted a, sorry, timer, wanted a 32-bit number. We give that 32-bit decimal number of that, and an output of match. We'd need to create a wire for match. And what this does is every 125 nanoseconds, match will be high. Strictly speaking, with this information, what we could do is have an always at block. And inside that always at block, we can see if match is high, then what we can do is we can move it all over. You could do that. What you could also do is we can instead steal the code from our shift register. A shift register takes in data, and every clock cycle shifts that data one bit over. So shift register. I don't like any of these diagrams. This is not bad. This is a bit confusing, but it takes in some data and it just shifts that data over by one bit every time the clock cycle passes. So what we can instead do is we can repurpose this. Because as we said, it says that the active LED should move from right to left, activating one at a time. What's basically happening is this LED is being shifted by one position. It's being shifted constantly. Instead of using a timer, so like we said, we can use our timer. We can say that every time this happens, we have an always at block. We say that if match, then we shift the LED. Alternatively, instead of a timer, we make a new model. Let's call this, what was it called? Shift underscore reg. Shift underscore reg. Next finish. Paste that here. Save. What we can see is that this is our shift register, which takes an input clock, input data in, and it has an output of data out. It has a register of data and the next data, and every time the clock happens, it loads in the next data, and the next data is controlled by this. It shifts the input left and inputs a new bit into the LSB over here. In our cases, we have 16 LEDs, so our output would be a 16-bit variable from 15 to 0. All our states should be 15 to 0. And then what we want to do is always the next state should be the equivalent of, we'll make that the last 14 bits of our digit. So let's say we had our current D equals that. Our next state should be equal to that, except the last digit is removed, it's shifted one to the left, and a 0 comes in on the end. When we keep shifting, it just depends 0 on the end. It moves one to the left, and a 0 comes in on the end. Moves one on the left, a 0 comes in on the end. In our case, we would start off with just one LED. We would have this. We have all our 15 LEDs. We have our rightmost one illuminated. Then after 125 milliseconds, the LED shifts to the left, and a 0 comes in. The LED shifts to the left, and 0 comes in. Does that make sense conceptually? Awesome. So what we can do then is, instead of actually taking a data in, the stuff that comes in on the very end is always a 0. So we can delete our data in input and just shove a 0 on the end here. Right? And then because we have 15 bits, this would be the first. We have a 16-bit variable, so we take the first 15 bits of our data, have that on the left, and then throw a 0 on the end. Does that make sense? Cool. So what this does is it shifts left and append 0 on the end. Cool. So what this would do, we also need a starting state. What we can have that as with our reset pin. So we'll take an input reset, right? So what it says is when the reset is high, it should start the sweep again from LED 0. So what we can do here is that if reset D equals 16 binary 1, we could do this and just pad it with the right number of zeros, or we can just say 1. It's smart enough to know what that means. If reset equals 1, do that. Otherwise, data equals data next. And that way, when we hit reset, it'll be loaded to 1, and then every time the clock cycle changes and the next state is loaded, the next state will be the current state, shifted 1 to the left with a 0 on the end. Does anyone see what the issue with this code might be compared to what the task asks for? There is one final issue to tackle. You don't count if anyone else has an idea. Any ideas? What's the idea? What's the answer? Perfect. Perfect. How do you reckon we can check for that? What would the if statement check? Perfect, perfect. So what we would check here is, so currently the next state is always shifted 1 to the left. What we would check instead is if LED, what does it say? If the leftmost LED, LED 15 is reached, if LED 15 equals 1, then D next equals D. It doesn't change, right? Just keep it on. If the leftmost LED is reached, then just stay on. Otherwise, our next state is shifted 1 to the left. Make sense? We can also, just for the sake of ensuring it's always on in case our inputs are wrong, we can just say 1B1 and then 14 or 15 B0. What this does is it's a 1 on the end and then 15 zeros on the right side. Cool. There is a syntax error on line 18. Oh yes, D next equals. Cool. And then D out is not what we want. We want our output to be our LEDs, right? We'd assign LED equals data. Am I missing anything? I think this looks good. We can write a test bench. Can write a test bench in 2 minutes. Speedrun challenge. All right. File name, test2. On our Q2, no, this is on our shift register. Finish. Load up. Come on. Okay. What we want to do is we just want a clock to go on forever, right? Actually, before I do that, we can't actually, we would use our timer in this to step our timer down to those 125 milliseconds. So using the timer that we implemented to step down, we can't simulate that because the simulation would take absolutely bloody ages to run. So we will ignore the timer component for now. When you're implementing it on your board, you will need to use a timer, okay? Cool. So in here, we will simulate our clock. In your real board, the clock's already provided, so you don't need to bother with that. But we'll have a forever begin, forever begin, and initial begin, and clock equals 0, and then forever after 100, or maybe 10, 5, clock equals not clock. What this does is it, every 5 nanoseconds, it toggles the clock. Make sense? Starts at 0, and then every 5 seconds, toggle the clock. And then here, we can set our reset to high, reset is 1B1. Wait, 100? We're actually working on a period of 5 in the clock cycle. Instead of waiting 100, let's wait like 10, maybe 11, just so that the reset finishes. Then what we can do is set the reset back to low, because when you reset it, it stays on the rightmost pin only. When the reset's off, then it can start doing its shifting. Reset off, and theoretically, this should just run by itself all the way to the end. And when it stays at the end, it should stop. If we run on test 2, okay, I hope so. Ooh, we have a lovely little error. Our clock is working. LED starts at 0, and then it never actually continues to shift. Let's do a little debug session. Shift reg. This sets the clock to 0. Sets the reset high. Ooh. Let's wait a bit. Simulate. Did I hit simulate? Okay. We also check what might be wrong with the code. Still doesn't fix it, does it? Ooh. Let's take a look at our code and see if we can do a debug session. We're passing in a clock, a reset, and an LED. We go here, what's wrong with our shift register? Take an input clock, reset, output 15 to 0, the LED. Register the data and the data next. On the positive edge of the clock, oh, anyone see what the issue is? We're not actually sensitive on the reset. We should also have reset here. Every time the reset changes, you should keep this in mind, not just when the clock changes, because the reset in our thing changed not exactly at the same time as the clock. There'll be an offset. We have that. If reset is high, data equals 1, otherwise data equals data next, and then we begin. If the current state, you shouldn't index it there, if the state 15 is high, then the next state should be the same state, otherwise shift 1 to the left. It should be good. Let's see, I hope it runs. I think it didn't. Ooh. Okay. I'm aware of the time constraint right now. But I think I have a saved copy of this when I did it yesterday night. Let's see. Can anyone spot the issue? Did you find the issue? The sim? Okay, let's load the working copy. We can see if we can play again or spot the difference. Task 2. Cool. Right, this is what I wrote last night. What's the difference? Okay. Well, let's try simulate. Ooh, even better. Woohoo! That's task 2. That's funny. Can you see the issue? We will be getting kicked out very shortly, so let me see if I can just find the screenshot. I think so. Are we not? How long do you have the booking for? Extra hour? Okay. this is the screenshot that I took last night of the working code here. Can we play game and spot the difference?
Wait, which the right hand side is to
This is my. Oh, so it's the code in the test bench. Yeah. Okay, and then this is our broken copy. Open project. Where do we save that order?
The one we just made.
Yeah. This is not it. Did I not hit save? Oh, I don't think did I not hit save? No. Open project. This isn't sample lab exam. Oh no, task. Oh, I made a new project, did I?
Yeah, you did. It's the one with the marks.
Oh wait. Oh, I made a stupid error. Okay. Sorry, what actually happened was I had the Verilog module by itself selected when I ran the simulation. This will not be a problem for you, but if you see here, there is the test bench and there is the actual task. I tried to simulate the actual task, the actual Verilog module. So it had no inputs, which is why everything was undefined the entire time.
Yo.
Whereas, if I select the actual simulation, the test underscore thing, and I hit simulate, there we go. All right. There we go. And now if we hover over that, perfect.
Oh.
There we go. Woo! Sorry. Okay, so as we can see, the clock starts, the reset is high for a while, and then the input just keeps incrementing until it reaches the very end, and it holds until we give it another reset, and the goes back to 0, and it starts climbing again until the very end, and it holds indefinitely because there's no more reset. Cool? Awesome. In that case, do we have this for another hour? Did he confirm?
Yeah, I did.
Does everyone want to try implementing another question, or I can't be bothered? Are you bothered?
But he sent off the question.
I can show you the question.
Yeah, what question?
Let me freeze it while I fish for the other question. Where do I have that? Would be in. We'll be right back. 24. Yeah, I got it here. Streaming screen. Can you hear me? Yes, you can. This unfreeze. Freeze images on? There you go. This was the question from last year's sample lab exam, which has changed for you now. But so you'll notice that most of the lab exam questions follow a very similar pattern of playing with the LEDs over time with either a shift register or a timer. So the sample question from last time was to create an LED ping pong effect. What it does, it basically does the same, shift it to the end, but instead of holding it at the end, shift back, and then shift again, and again, and again, and again. And it just plays ping pong back and forth. And in the simulation, it should look something like this. So you'll see here the LED climbs from 0 all the way to 6, and then back down to 0, and then up to 6, and then back to 0, and up to 6 again, based on our clock. And I don't think you all want to see me live code it, but I'll give you a solution in case you want to try it yourself and then compare. This is how I implemented it. So it takes in the clock, the reset, a match, and an LED. This match is strictly not necessary. It has a variable that stores which direction it's currently going in. It takes in our timer. Like we said, the timer slows it down because the question asked us to do a cycle of every 2 seconds, whereas the system clock is every, oh yeah, we just freeze it there. All right, so it asked us to do a cycle every 2 seconds, but the system clock is every 10 nanoseconds. So we use the timer to step down our clock. The current value gives a period of 2 microseconds. We want 2 seconds, which is a factor of 1,000,000 times. Hence a delay of 10 million divided by 7 for the 7 different LEDs is the period that we need. We take the timer, we give it in our clock and our reset as expected. Our delay period is 100 divided by 7. And our match, using that match, whenever it is matched, if it is a reset, then we set it to set the LED back to the right hand side and start the process again. Otherwise, if it was a match, and so this is where it gets a bit complicated. This syntax has not been covered yet, but this is a bit shift. This basically does what we just did with the curly brackets and a 0 at the end, but in one line. What it does is it takes the LED, it literally shifts it one to the left, and then throws a 0 in the end. Whereas the one with the arrows pointing to the right takes the value, shifts it one to the right, and throws a 0 on the right, on the other end. Cool? No, it doesn't actually loop around. It just throws an extra 0 at the end. So if you're shifting it all to the left, it moves the code the numbers that you have one to the left, and it adds a 0 at the end. And it moves again and adds another 0.
So same thing, but like they can manipulate the direction.
Yes, yes. So the arrows point in which direction the numbers go. So if I had exit, so if I had like, let's say I had that, and I shifted this one to the left, this would go and a 0 on the end. And another left shift, it would go and a 0 on the end. Now the left shift, it moves to the left and a 0 on the end. Whereas if I right shifted, and I had back to my all of that, if I right shifted, all of this would move to the right. So the right hand side is lead and a 0 on the other side. Another 0 and it gets moved. And another 0 and it gets moved. Another 0 and it gets moved. Cool. And if you keep going too much, you shift over, you'll just get zeros infinitely. And it's just like an infinite loop of zeros. Based on this, what this does is if we are at the rightmost LED, then do not reverse. Whereas if we're at the leftmost LED, then work in the reverse direction, right? Because we're playing ping pong back and forth. And then based on the reverse direction, either shift left or shift right. Cool? So like the actual implementation of that question can be done in these lines. I'm sure someone will find a way to make it even shorter, but I think this still makes a little bit of sense. Are there any questions about either this code or the previous task's code or any other questions?
Could you explain the part with the time, the local param?
So local param is another way of just declaring it's not a variable, it's like declaring a constant. Have you done comp 1511? Do you remember hash defines? We have a constant and we give it a value that never changes. Just like that, local param is a constant value that never changes. And we calculated that we need a delay period of 100 on 7. And we set that as our thing. Cool. Any other questions? Does Otto have a question for me?
Just a quick question, sorry.
Question.
For the task one we dealt before, like sorry, the one for us for the question two.
Oh, yeah.
What do we do for timer, or we're just not using timer for that one?
So you would. So when you're actually making the code, you can see my calculation here is that apparently the clock then had a period of 2 microseconds. You are given a data sheet, right? Here you're given the reference manual. Inside your reference manual, if I control F for clock, there we go. The Basis 3 board includes a single 100 megahertz clock on pin W5. So based on that, you can calculate the period of your clock, and based on that, you know that the period that you want was, I think, 2 seconds, right? No. Was it 2 seconds? 125. There we go. It was a period of 125 microseconds. So based on that, you would do the calculation of how many periods are in 125 microseconds. We can do that now. 1 on 100 megahertz is a 10 nanosecond per clock, and you wanted 125 microseconds divided by 10 nanoseconds, and that would be your delay number. So my delay number was 100 on 7. Your delay, right? Your delay number would be what's that? 12.5 million. Cool. So you would call the timer in basically the exact same way, except your delay is 12.5 million instead. And what this does is every 12.5 million clock cycles, or every 125 milliseconds, match will go high, and the always at block will trigger.
Well, why is there no timer in your code then?
Oh, the timer is the same timer module. As in,
Oh, it was just internal.
yeah, you just, no, you'd copy paste it from here. This timer.
Yeah. Oh.
You just copy paste this timer as your timer.
Change the number. Okay.
Yeah. So as you see, the clock reset duration match.
Okay.
So please, in your lab exam, do not write a timer from scratch. It will probably not work and you'll waste all your time. Just, these are provided to you in some way or form. Maybe like it's already there or they let you on paper. I don't know. It's given to you, use them.
So just to clarify, you use timer instead of clock, right? Or no?
What do you mean?
As in your code.
Yes. Can you think why?
Because you don't want 100 megahertz.
Precisely. So this timer basically kind of slows our clock down. Cool. Any other questions? Does anyone like want me to code anything up else up? A decoder? I don't know. An AND gate. No? All right. Good to go? All right. Thank you for coming. Let's actually take a quick photo, hey? Thanks for coming on the stream. Or is anyone actually watching the stream? For watching on the stream. All right. For anyone who watches the recording,